invitation. I have two roles in this panel. The first role is I'm the chair of this panel, and the second role is to deliver a presentation. So in this interesting panel, which concerns actually the role of dispatchable renewable energy technologies in the competitive electricity market, we will have two presentations, and then a panel discussion will follow. We will have with us Dr. Luis Crespo, Dr. Charles Kutscher, Dr. Nestor Phylaktos, and Mr. George Partasidis. So I suggest when the presentations are completed, that all the panelists will take their seats on the panel in order to start the discussion. Okay, so let me start with my presentation, which concerns the large-scale integration of renewable energy systems into the electricity markets. Here is the outline of my presentation. First, I will present you briefly the European Union energy strategy towards 2020, 2030, and the long-term strategy towards 2050. I will then present you the challenges in the electricity markets concerning the large-scale integration of renewable energy sources, the role of the natural gas, and also the role of storage. I will close this presentation with the modeling for optimal large-scale integration of renewable energy sources, including storage. Now, we are at the beginning of the third energy revolution, a revolution that will come at a cost to the end users in comparison to the previous two energy revolutions, which became at the benefit to the end users, to the customers, and this is mainly due to the climate change. So the economics of the future energy systems become very important. The European Union have already set its objectives. The main objective is the reduction of the greenhouse gas emission, by 80% till 2050. And in order to achieve this, we need to produce and to consume energy in a sustainable way. And in order to decrease this rate of increase in the energy cost, the electricity and the natural gas markets in the European Union are open to competition, and also taking into account always the security of supply. Here I show you in summary the medium and the long-term targets of the European Union. We are all familiar with the 2020 we are all familiar with the 2020 package, which calls for 20% reduction in greenhouse gas emissions, 20% increase in the use of renewable energy sources, and 20% increase in the energy efficiency. Now, the so-called 2030 package, or the European Union package, calls for 40% reduction in the greenhouse gas emissions, more than 27% renewable energy use. This is mainly around 32% now, and also greater than 27% energy increase in the energy efficiency. And of course, the final target is the reduction of the greenhouse gas emissions by 2050 by 80%. Now, what I show you here, I show you the different energy sectors' contribution towards the reduction of the greenhouse gas emission. And what do we observe? We observe that the power sector, by 2050, we expect zero emissions from the power sector. The remaining 20% emissions will come from the industrial sector, the transport sector, and the other sectors of the energy. So, our energy future is 3D. And what do you mean by 3D? Decarbonization of the energy sector, decentralization of the energy sector, as well as digitalization of the energy sector. So let me just show you in 3 slides the current energy system of the European Union and how we can convert this energy system to a more sustainable one, to a system towards hydrogen economy. This is an optimistic scenario, of course. Here I show you the energy system of the European Union as it is today. The black line concerns oil. We have oil used in every sector of the economy, for domestic use, for transport use, for industrial use, as well in some member states for power generation as well. Now, the green line concerns the natural gas. Natural gas, again, is used in all sectors, again, in the domestic industrial sector and for power generation as well. Of course, for power generation, electricity is the blue line here. In European Union, we also use coal, nuclear power, and in some cases, oil. Now, the first transformation in this optimistic scenario towards the hydrogen economy, we have between 2030 and 22 and 2030 the first transformation. We observe that oil is used only in the transport sector. We have natural gas, which will be used in all energy sectors. We have the appearance of the hydrogen communities. That means communities that are self-sustained in electricity using renewable energy sources, and the surplus of electricity can be actually transformed into hydrogen, and then hydrogen can be used in the regional hydrogen distribution networks. Also, we will have the appearance of the hydrogen plants, hydrogen power generation plants, using mainly hydrogen coming from reforming natural gas. And finally, in this optimistic scenario towards hydrogen economy, we have between 2040 and 2050 the complete transformation of the European energy system to a more sustainable one. Oil disappears from the scene. Natural gas will still be used in the industrial sector, and then we'll have hydrogen in all sectors of the economy. We expect the appearance, of course, by that time, of hydrogen airplanes as well, and also the establishment of the hydrogen communities. Now, what about the future power systems? Today, we produce electricity in central power stations, and the electricity is transmitted through the transmission network and the distribution network to the end users. Now, the future power system is more complicated. This is a smart power system. The innovation in this power system are those red rectangles, which concerns storage. Storage either from batteries or from any other technology. And this, by doing this, we can then transform the intermittent renewable energy sources to dispatchable energy sources. For example, during the night, when there is high potential of wind in some areas, especially in Cyprus, we cannot commit the wind parks due to the technical problems that may create in the electricity system. However, with this arrangement, the wind parks will be committed, will be produce electricity, and then electricity can be stored either in batteries or maybe hydrogen, producing hydrogen, and then during the day, the stored energy can be used in order to meet the peak demand or in the transport sector. Also, the central power stations will be used. However, it will be used in a different way. They will be operate in high capacity, 24/7, and the excess electricity produced can then be stored and then used during the day in order to meet the peak demand or in the transport sector. And of course, the electric cars are one of the challenges that we are facing from today, how to integrate large-scale integration of electric cars as well. So the end goal is a smart future, a future in which we will have smart electricity and natural gas network, And also we expect by or after 2050 the appearance of the super smart grid. This is a grid, a smart grid that will connect Europe with MENA countries, the North Africa and the Middle East countries, and the renewable energy sources will be installed in areas in which the potential is high. For example, we all know that wind potential is high on the North Sea and also on the west coast of Europe, as well as in the west coast of North Africa, and also in some areas in the Aegean Sea, for example. Also, the CSP technologies are well suited within the North Africa area and the Middle East area as well. Also, photovoltaics are suited actually in the South Europe area, as well as in some areas in the North Africa countries, and also hydropower where the potential is available, biomass where the potential is available, and also the use of marine technologies and geothermal technologies as well. So by having all this integrated with storage, we may reach 100% renewable energy sources power system by 2050 or after 2050. So we have a vision from the European Union concerning a carbon-free Europe by 2050. We have many ingredients concerning the future sustainable energy systems, the integration of renewable energy sources, storage, hydrogen, electric cars, and so on. So we need to develop advanced simulation tools, new sustainable technologies and infrastructure. And this is the main reason why the European Commission have already increased the funds concerning research in energy in order actually to invent the technologies for the future. So let's move on now to the challenges concerning the integration of renewable energy sources into the electricity markets. Here I show you the European Union electricity market target model. This is actually the electricity market model that it is used in most of the European Union countries. This consists actually of 4 parallel markets: the forward market, the day-ahead market, the intraday market, and the balancing market. I will not go into the details of this model. However, one of the challenges is to integrate into this target model the renewable energy sources. Now, in the literature, there is a confusion actually concerning the comparison of renewable energy sources with conventional technologies. Most of the literature concerns with the levelized cost of electricity and neglect reliability of the system. However, in order to be fair, in order to have 24/7 electricity in all customers, we need to take into account reliability of the system as well. And what do we mean about reliability? We mean adequacy and security. Adequacy is the power system ability to satisfy customer needs, both in power and electrical energy, 24/7. And also security is the power system ability to remain in operation after sudden disturbances. On the other hand, we know that most of the renewable energy sources are intermittent energy sources. That means sources that are not continuously available, such as wind potential, for example. There might be quite predictable, such as the solar potential. However, they cannot be dispatched into a given power system in order to meet the demand of the system. And this is why we need reserves in order actually to back up in case that we do not have enough potential, either solar potential or wind potential at that particular time. And this, of course, increases the cost of the system. In order for these technologies to be dispatchable, we need to integrate storage into the system. And also, we need to integrate flexible technologies as well into the system. And I will explain what we mean by flexible technologies in the following 2 or 3 slides. Now, here I show you the daily load curve that the transmission system operators, the TSO, are used actually today. We have 1 or 2 humps during the day. So this is quite predictable. You know from the previous day that the load will actually follow that profile. Therefore, we can then decide which units to be on load and so on. However, by the integration of renewable energy sources, and especially in this case, I show you the integration, large-scale integration of photovoltaics, this camel curve becomes the duck curve. What do we mean by duck curve? This is the belly of the duck, actually, and the blue color here concerns the production from photovoltaics. Now, in this case, the problem that we have, that we will face in the future, concerns this sudden increase in the load that the conventional technologies need to take up, actually, when the solar potential will be reduced during afternoon. The technologies that we are used today, especially steam turbines, for example, are not capable, the technical characteristics are not capable actually to catch up so high degrees of load. This is why we need flexible technologies as well in combination with storage. Here I show you the use of natural gas in order actually to absorb all these ups and downs from the renewable energy sources. The natural gas technologies are, the technologies that are using natural gas, actually, the combined cycle technologies or the gas turbines technologies are flexible technologies, as we call them, because they can move up and down the load in minimum time. So here I show you simulations from the Oxford Institute for Energy Studies concerning 2009 in UK. We have here this is a poly here. We have the production from nuclear, the production from coal, the production from natural gas, and a small production from renewables. However, the situation is expected to change in the UK, and we expect by 2025, especially to have large-scale integration of wind technologies. So we expect that all these up and downs from the wind technologies will be absorbed from the natural gas technologies, from the combined cycles and the gas turbines. So this is the first ingredient that we need for the integration of renewable energy sources, natural gas. And the second is the storage that I have already mentioned before. We have identified the various types of storage that can be used at the different markets within the European Union target model, and we have already started performing simulations and so on. Now, let's move on to the modeling for the optimal large-scale integration of renewable energy sources. Now, the need actually is the large-scale integration of renewable energy sources, of course. And the main objective is to assess, at the end of the day, the increase or the benefit, if there is benefit, depending on the power system, in the cost of the electricity for a given power generation system at different renewable energy sources penetration levels. In order to achieve this, such modeling need to use unit commitment algorithms, need to take into account the existing energy mix, and also to include storage, and then to calculate the cost or the benefit in the cost of electricity. In the case we have cost, then to be able to calculate the price of the feed-in tariffs of the feed-in premiums, for example, and also the green tax that it is required in order to support this large-scale integration of renewable energy sources. This is a typical objective function that we minimize. However, this objective function here depends on many constraints. These constraints are related to reliability that we mentioned before. Load demand constraint, unit capacity constraint, available capacity constraint, reserve margin constraint, and so on and so on. And of course, we need actually to find the optimal solution. In this slide here, I show you on the vertical axis the electricity unit cost. So we minimize for the electricity unit cost, taking into account the reliability of the system. And on the horizontal axis are the different combinations between the existing system and the various integrated renewable energy sources, the candidate renewable energy sources, or any other technologies, storage, for example, or conventional technologies. So we seek actually to find the solution not at the local minimum, but the solution at the global minimum. Here I show you an optimization model that we have developed during the past years. Just in brief, here we optimize each candidate technology, either renewable technology, conventional technology, or storage technology individually, and then the optimum parameters are fed into this model here, in which we take into account the existing power system. Then we will be able to calculate the optimum generation system electricity unit cost, taking into account the externalities, CO2 emissions. And in the case that we have a cost, we can then calculate the relevant feed-in premiums, for example, and the green tax. Or in the case that we have a benefit, then we can forecast the electricity price for the next 10 years. This is the final objective factor that we minimize. I will not go into details. Let me show you some results. This is a study that we have carried out for the United Arab Emirates a few years ago. Here we have actually investigated the use of photovoltaics and the use of CSP technology, concentrated solar power, with no thermal storage, and by integrating storage at different degrees of storage, up to 24 hours per day operation. As expected, the electricity generation from the CSP with 24 hours per day operation is the highest, of course. Now, we have also calculated the CO2 avoided emissions as well. But the most important, we have calculated the levelized cost of electricity, parametric curves. And what do you mean by this? This curve here concerns photovoltaics at different capital cost values, and the vertical axis is the cost of electricity. Here we have the parametric curves concerning the CSP technologies. This concerns the CSP technologies at different capital cost levels with no thermal storage, and this one with 24/7 thermal storage. So we actually observe that CSP under certain conditions can be an alternative to photovoltaics, and also with reliable electricity. And we have also identified the profiles during the summer and during the winter from those technologies. For example, here I show you during the summer. The red line concerns the production from the photovoltaics. This is a 50 megawatt photovoltaic plant and 50 megawatt CSP plants. The blue line here concerns the CSP profile from without also thermal storage. And of course, with 24/7, we have this profile here during the summer. And of course, during the winter, we have different profiles, and this is a 24/7 profile during the winter. And finally, let me just show you the integration of storage into a power system. Here I show you on the vertical axis the total production cost from a given system for the whole year. What do we observe? We observe that during low renewable production, the red line concerns the cost when we have the conventional technologies as well as the photovoltaics, and the green concerns the conventional system without renewables. We observe that during low res production, we have a benefit to the system. That means that renewables reduces the cost of the system. However, during high renewables production, we observe that the cost the total production cost of the system increases, and this is because of the reserves that it is required in order to back up the renewables. However, by integrating storage, we observe that this is actually week 36. This is the peak here. What we observe that this is the cost of the system when we have only conventional technologies. This is when we have conventional technologies and renewable, and the blue line concerns when we have conventional technologies, renewables, and integration of storage. What do we observe? We manage actually to reduce the cost of reserves by using storage. I will close this presentation at this stage in order to stimulate the discussion later on. Thank you very much.